The European Centre for Particle Research, CERN, is unveiling details of a new particle accelerator today.
Right now, beneath the Alps, near the city of Geneva, Switzerland, there is a tunnel. And machinery inside that tunnel sends beams of energy in a vast circle, so big it would take you nearly 6 hours to walk around it just once. And then it crashes them into one another.
The European Council for Nuclear Research, known for its groundbreaking discoveries in particle physics, has long been at the forefront of scientific exploration. Situated deep underground, researchers like Steve Myers continue to push the boundaries of our understanding of the universe. However, recent findings at the research facility have raised concerns about the potential creation of a wormhole in Europe. Join us as we delve into the consequences of this discovery and discuss why it's crucial to be prepared for any potential disaster that may arise. The particle pursuit. Scientific progress is clearly a big achievement for humanity. Yet there are times when the discoveries made by scientists are ahead of what the public can comfortably accept. Consider the European Council for Nuclear Research, better known as the European Council for Nuclear Research, which has been pushing the boundaries of our knowledge about particle physics since it was established in the 1950s. The European Council for Nuclear Research has often been at the center of attention, praised for its groundbreaking work, but also viewed with suspicion and fear of what its experiments might unleash. The research done here isn't just for academic interest. It questions and sometimes shakes our fundamental ideas about the universe's workings. Some critics worry that the particle collisions in the Hadron Collider could have unexpected and uncontrollable effects. Even with scientists ensuring that safety measures are strict and the risks minimal, there's still widespread anxiety about the outcomes of these experiments. This fear typically comes from not fully understanding the science involved and is amplified by how the media reports these scientific efforts. The European Council for Nuclear Research plays a vital role in the scientific community, making incredibly important contributions. However, the apprehension accompanying each of its announcements points to a gap between how fast science is moving and how the public feels about these advances. The European Council for Nuclear Research operates at the intersection of theory and reality, where each discovery could potentially change our understanding of everything around us. The skepticism towards new scientific findings isn't just about resisting new information. It reflects wider worries about how quickly science is progressing and what that means for us all. In an era dominated by evidence and technology, the uneasy relationship between discovery and public readiness is always there. As we venture further into the unknown, maintaining a conversation between scientists and the public becomes essential. If this communication breaks down, every new scientific finding could be met with distrust and fear rather than curiosity and excitement. The Large Hadron Collider, despite its groundbreaking aims, sparked considerable debate. With a staggering cost of over $4.5 billion, this massive particle accelerator stretches 27 kilometers across European soil. It represents a significant investment in the pursuit of advanced scientific knowledge, primarily in physics. Yet it begs the question, was this monumental expenditure necessary? Supporters of the Large Hadron Collider see it as a critical hub for scientific advancement, where elusive theoretical particles and fundamental forces of nature come under rigorous examination. Many critics argue that the vast sums invested in the Large Hadron Collider could have been better spent addressing more pressing global issues or supporting broader scientific inquiries that offer more direct benefits to society. Instead, the funds were channeled into a project whose benefits, while academically significant, offer little in terms of immediate practical applications. In addition, the Large Hadron Collider has identified numerous previously unknown particles, further complicating the field of particle physics. Each discovery, while exciting for physicists, often leads to more questions rather than simplifying our understanding of the universe. This ongoing complexity can make the Large Hadron Collider seem like an elaborate puzzle that consumes enormous resources without offering clear, tangible benefits. The Large Hadron Collider symbolizes what can be achieved with generous funding and dedicated scientific exploration. It showcases human curiosity and our desire to understand the fundamental aspects of our universe. However, it also highlights the disparities in funding allocation within the scientific community, where such ambitious projects are feasible only with substantial financial backing, potentially at the expense of other worthy scientific or humanitarian efforts. This large particle accelerator works by pushing various particles around a circular track so fast that they nearly reach the speed of light, circling more than 11,000 times every second. This is possible thanks to several very strong electromagnets. These magnets produce a magnetic field within the accelerator that is over 1,000 times stronger than the Earth's natural magnetic field. Many people have started to worry about the possible effects of creating such a strong magnetic field. Let's think about what happens when we push technology too far, probing the dark limits of scientific responsibility. Moreover, the power of these electromagnets, while impressive, has raised questions. Some argue that we need to think carefully about the consequences of our actions on a larger scale. Just because we have the ability to manipulate such powerful forces doesn't necessarily mean we should. The risks of causing damage either to our electronic systems or to the Earth's magnetic stability are real. The science community is closely watching these developments. They are trying to balance learning more through these experiments and being careful not to cause harm. The discussions among scientists, engineers, and the public reflect a bigger challenge. How do we handle new technologies responsibly? These discussions become even more pressing as the particles are accelerated to their highest speeds. People on both sides of the argument, those pushing the boundaries of what's possible and those urging caution, continue to debate the best path forward. This ongoing conversation highlights our complexities and responsibilities as we explore and manipulate the natural world. Particles racing at nearly the speed of light are smashed together in an intense collision designed to unleash a massive amount of energy and create a storm of new, short-lived particles. This orchestrated chaos is not random, but a carefully planned scientific experiment to uncover the universe's inner workings. The particles chosen for these collisions are not random. They are carefully selected in hopes of observing something new amid the aftermath. Around these collision zones, sophisticated detectors are strategically positioned to capture every detail from these high-energy encounters. The amount of data these detectors collect is enormous. They are crucial in gathering evidence from the collisions, which often present more questions than answers. These detectors demonstrate human creativity and our desire to explore and understand the smallest components of our world. Changing the types of particles used in collisions is like experimenting with different ingredients to see what reactions they produce. Scientists examine the results closely using advanced technology, hoping to spot an unknown particle that could explain deeper truths about how everything in the universe works. One might question whether smashing particles together is the most effective way to discover the unknown. While it shows our ability to manipulate and probe nature, it also reflects a somewhat brute force approach to learning about the universe. Though technologically sophisticated, each experiment could be seen as a bit of a gamble, relying heavily on chance and the hope of catching a glimpse of something unprecedented. As these collisions occur, the detectors do more than just record data. They capture the essence of human curiosity. In their relentless search for new particles, scientists use these tools to peel back layers of the atomic world, hoping to find clues about the universe's fundamental structure. This pursuit, driven by both ambition and a bit of arrogance, pushes the boundaries of what we know and how far we are willing to go to learn more. The scale of these experiments is enormous, involving vast amounts of energy and intricate machinery, all to observe particles that exist for only a blink of an eye. The fleeting nature of these particles adds to the challenge, as does the complexity of the data collected. The quest to understand the universe's building blocks involves deciphering this data, which often requires as much intuition as it does scientific knowledge. Despite the high costs and the sophisticated technology involved, the drive to conduct these experiments speaks to a fundamental human trait, the thirst for knowledge. Each collision offers a potential window into previously unseen aspects of matter, providing glimpses that, although brief, have the potential to revolutionize our understanding of everything from the tiniest particles to the vast cosmos. The Large Hadron Collider is an impressive machine that produces a staggering amount of data, 15 petabytes every year, all from smashing particles together. That's a vast sea of information, and it's a massive task to sort through it all. Imagine needing a whole team of skilled physicists and data experts to pore over this data, hunting for valuable scientific clues. In 2017, a significant event took place. The Large Hadron Collider's data storage hit 200 petabytes. To put this into perspective, 1 petabyte can store about 250,000 movies. This comparison highlights the immense scale, but doesn't simplify the complexity of what the data actually contains, or the huge effort needed to extract meaningful science from it. What are the researchers looking for in this vast amount of data? They're not just randomly searching through numbers and charts. They have specific goals, like uncovering new particles that could tell us more about how the universe works. For example, the discovery of the Higgs boson in 2012 was a result of this kind of data analysis. However, one might question whether the intense effort and resources poured into parsing the findings balance this data. The scientific breakthroughs are crucial but come slowly, emerging after years of detailed examination. Looking at this enormous task, one could see it as both exciting and overwhelmingly challenging. Each experiment at the Large Hadron Collider is like throwing a dart in the dark, hoping it lands somewhere significant. The data is potentially full of important insights, yet the sheer volume makes it like looking for a few grains of gold in a vast beach of sand. The pursuit of scientific knowledge here is marked by a scale of effort and ambition that is as daunting as it is admirable. Every small step forward in understanding requires a giant leap of effort. The struggle for progress in particle physics is a constant test of patience and persistence. It's a demanding journey that requires state-of-the-art technology and a relentless commitment from the scientific community. Each discovery, no matter how small, is a victory in the face of these challenges. But the road to each discovery is long and filled with obstacles, requiring a commitment that goes beyond the ordinary, pushing the boundaries of human knowledge and endeavor. This makes one ponder the balance of effort versus reward in high-stakes scientific ventures. The commitment to uncovering the unknown drives the scientific community forward, tirelessly sifting through data in search of the next big revelation in our understanding of the universe. Now, let's see how these new findings could shake up our understanding of physics. A new wrinkle in the fabric of the cosmos. As researchers explored the tiny world of particles, they stumbled upon something unusual with the beauty quark, one of the many types of quarks that make up everything around us. Quarks are incredibly tiny particles that come in different varieties, each with its own characteristics. The beauty quark is particularly noteworthy, not just because it exists for an incredibly short time, about 1.5 trillionths of a second, but also because it didn't behave as scientists expected. This unexpected behavior wasn't just a simple surprise, it was a significant challenge to the accepted theories. Typically, scientists have a set model called the Standard Model, which predicts how particles like quarks should act, including how they transform or decay into other particles. But the beauty quark broke these rules, showing a pattern of decay that didn't fit the predictions. This odd behavior suggests there might be flaws in our current understanding of particle physics. It's a bit like finding a puzzle piece that doesn't fit where it's supposed to, according to the box's picture. This has led to a lot of head-scratching and rethinking among physicists, who now wonder whether there might be elements or forces affecting these particles that they haven't discovered yet. The issues with the beauty quark's behavior raise bigger questions about other parts of physics that might also be off in ways we haven't noticed yet. It's as if scientists have been using a map to navigate, and suddenly they find themselves at a dead end that isn't supposed to be there. This prompts a reassessment of the map itself. Perhaps it's time to redraw it, or consider what else might be missing. Moreover, the anomaly invites a more extensive investigation into the beauty quark and all related particles and forces, pushing the boundaries of what we know. It encourages scientists to be more skeptical of established theories and to keep testing and questioning even what seems certain. This is how science progresses, through continuous questioning and refining of our knowledge. This situation with the beauty quark is a clear reminder that in science, nothing is ever completely settled. Each anomaly is a doorway to new discoveries, urging the scientific community to keep an open mind and to explore further. It's an exciting, though challenging time for physicists as they work to uncover more about the universe and possibly rewrite some fundamental principles of physics. In the detailed and often challenging field of particle physics, the data from the Large Hadron Collider has revealed an unexpected pattern that has sparked debates and speculative discussions among scientists. According to the well-established standard model of particle physics, certain quarks should transform into leptons, specifically electrons and muons, at about the same rate. However, our data shows a different pattern, with these quarks turning into muons around 70% more often than into electrons. This unexpected behavior challenges our current understanding and suggests that our theories might need some updates. The core issue involves the weak force, one of the fundamental forces that influence the decay of subatomic particles. According to standard theories, this force should treat electrons and muons similarly when it comes to the decay of these quarks. However, the data doesn't match this theory, proposing that there might be a preference that the standard model doesn't predict. This discrepancy raises the possibility that an unknown particle might influence these decays, possibly representing a new type of force. Some researchers, possibly motivated by the excitement of a potential discovery, suggest that this could mean there are new aspects of physics to explore. The idea of discovering a new particle that carries a new force is appealing, as it could significantly expand our understanding of the universe and mark a significant milestone in the careers of those involved in the discovery. However, submitting such a groundbreaking idea based on the current anomalies needs careful consideration. Particle physics is an area where extraordinary claims are supported by extraordinary proof, and often what seems like a significant discovery may turn out to be a result of experimental mistakes or statistical errors. Critics call for a more cautious approach, recommending a detailed examination of how experiments at the Large Hadron Collider are set up, how data is collected, and how it's analyzed. Similar anomalies have led to improvements in how experiments are conducted rather than new theories. Moreover, the highly complex equipment and extreme conditions under which these experiments are conducted mean that observed anomalies might be due to limitations or oversights in the experimental setup. Yet, the idea of a new particle is still an exciting one. If such a particle does exist, it would mean revising our understanding of the weak force and possibly other parts of the standard model. This could lead us to better understand the fundamental forces that shape our universe, possibly moving us closer to a comprehensive theory that integrates all known forces, including gravity. As the scientific community continues to sift through the data and debate its meaning, the path forward is filled with uncertainties. The excitement of potentially discovering new physics often leads to premature speculation, but science fundamentally relies on solid evidence and rigorous validation. Whether this anomaly will turn out to be a minor statistical blip or the doorway to new scientific principles will be resolved with more data and time. The excitement about possibly discovering new physics reflects a deep human desire to understand the world at a more profound level. theoretical physicists and experimentalists continue to work hand in hand, using the Large Hadron Collider and other tools to probe the fundamental constituents of matter. Each experiment, whether it confirms existing theories or uncovers new phenomena, adds a piece to the universe puzzle. The journey of discovery is long and complex, often filled with more questions than answers. However, each finding, whether it confirms our current understanding or challenges it, is a valuable step forward in our quest to understand the cosmos. What happens when the rules we know don't fit the facts? Quest for the complete universe. Surprisingly, the standard physics model, often seen as the top theory for understanding tiny particles, doesn't explain everything. It does a great job describing three key forces: electromagnetism, which involves the force between electric charges, the strong force, which holds the nuclei of atoms together, and the weak force, which plays a role in radioactive decay. Yet it completely misses gravity, the force that pulls objects toward each other, which is essential for explaining how things move on Earth and in the cosmos. This glaring omission points to a significant flaw. How can we rely so heavily on a theory that leaves out such a fundamental aspect of nature? Physicists might praise the standard model for its accuracy in certain areas, but this praise seems a bit too generous, considering it ignores gravity. This oversight is like praising a map that shows every small road, but omits the highways. Moreover, this gap in the standard model means that it's probably just a temporary solution, waiting to be replaced or expanded by a better theory. It's a bit like using a placeholder in a puzzle where the missing piece is too obvious to ignore. Despite this, the quest for a better theory has been slow. Physicists are searching for a new model that includes gravity and perhaps other forces or particles we don't yet know about. This new theory could revolutionize our understanding of the universe and answer many questions that the standard model can't touch. The standard model is like an incomplete story or a book missing its last chapter. It gives us a lot of detail and has been useful, but it's not the whole picture. We're still waiting for a theory that can give us a complete narrative of the physical world. For now, the scientific community recognizes the standard model as an essential tool, yet incomplete. The drive to find a more complete theory is motivated by the need to fill in the blanks left by the current model. But moving beyond the standard model has proven difficult. It requires new ideas, and perhaps a bit of a push to move beyond the comfort of the familiar, to explore theories that might seem unconventional today. As time goes on, the hope is that new discoveries will prompt updates to our current theories, much like software updates on a computer. These updates would ideally add gravity and possibly other elements into the mix, providing a clearer, fuller picture of how everything in the universe works. Until then, we continue to work with what we have, knowing that our current theories are more like sketches than final paintings. The challenge for future physicists is not just to tweak these sketches, but to possibly rethink the entire picture, opening up new ways of seeing and understanding the surrounding universe. Recent experiments have uncovered a discrepancy in the data that stands out sharply against what we normally expect from the standard model of particle physics. Given the vast amount of data it produces, it's not unusual for the Large Hadron Collider to generate results that don't quite fit the usual theories. However, this particular discrepancy caught the researchers' attention, and they couldn't just write it off as another minor statistical oddity. This anomaly points to a matter that doesn't fit our current understanding of dark matter. It suggests a difficult situation for physicists. Instead of bringing excitement, this discrepancy reminds us of the limitations of our current models and the often exasperating nature of high-energy physics, where new questions frequently arise without clear answers. Now, researchers have to revisit this anomaly, getting sucked back into a familiar cycle of forming hypotheses and testing them, a cycle well-tread in scientific communities, but one that rarely opens the door to revolutionary discoveries. In their efforts to make sense of this unexpected find, the researchers pondered whether it might suggest new physics, hinting at the edges of what we know and don't know in particle physics. They entertained the idea that we might just be seeing a small part of a much bigger picture, perhaps indicating new particles or interactions that previous models had missed. However, there is a strong sense of skepticism, as proving such theories is incredibly challenging, both experimentally and theoretically. The history of particle physics is filled with similar anomalies that seemed promising, but ultimately didn't lead to significant changes in fundamental theories. Each potential discovery undergoes intense scrutiny and often concludes as a reflection of errors in how data was collected or interpreted, rather than as evidence of new phenomena. Thus, researchers continue their work, aware that today's deviations could be explained tomorrow by tweaks to existing theories or technological advancements. The anomaly isn't just a potential lead into new scientific territories. It's also a reflection of scientific research's complicated, repetitive nature, where every solution seems to unravel more questions. Whether this leads to a major shift in our understanding of dark matter or merely becomes a minor point in the history books of physics remains to be seen. The ongoing work at the Large Hadron Collider is a constant reminder of both the potential and the limitations of our quest to understand the universe on a grand scale. Adding to the complexity, the scientists involved must navigate a web of technological and methodological challenges. Each piece of data must be meticulously analyzed and reanalyzed, often leading to long periods of doubt and debate within the scientific community. This rigorous verification process is necessary to ensure that any claims of new discoveries are well supported and reliable, adding layers of complexity to an already daunting task. Moreover, the very nature of exploring such fundamental questions about the universe entails facing vast unknowns with limited tools. Each experiment at the Large Hadron Collider is like looking for a needle in a haystack, where the needles are potential new scientific truths hidden within mountains of data. The painstaking work of sifting through this data, forming theories, and then testing these theories underlines the slow, often frustrating pace of progress in physics. As we dig deeper, each discovery challenges us to think harder and do better. The undercover hunt for Z prime. While discovering this anomaly is intriguing, it also serves as a sober reminder of the challenges ahead. The path to new discoveries is not only paved with data and theories, but also with persistence, skepticism, and an ever-present awareness of our own limitations. The quest to expand the boundaries of our understanding is a relentless pursuit, often requiring more patience and resilience than celebrated moments of breakthrough. The recent buzz in the physics world about a newly proposed particle named Z prime, which is described as a potential new force carrier, has sparked a lot of conversation. This particle is intriguing because it's said to interact in unique ways with electrons and muons, two well-known particles in physics. However, this claim should be met with some skepticism. It's important to remember that if this force were significant, we probably would have detected signs of it much earlier. The discovery of Z prime is being pitched as a major breakthrough that could drastically alter our understanding of fundamental physics. Yet, this isn't the first time the scientific community has been abuzz with excitement over a potential discovery that later turned out to be less than initially hoped. Given that Z prime is supposed to interact differently with some of the most studied particles in physics, it's surprising that it has managed to stay under the radar with all the advanced technology at our disposal. Researchers are excited because they believe Z prime could explain some of the lingering questions in physics. But the reality is that the impact of Z prime on the Standard Model, which is the theory describing the most basic elements of matter, is still not well understood. This leaves plenty of room not just for discovery, but also for doubt. Is it possible that what we're seeing in the data is just noise rather than a signal of a new discovery? Moreover, while physicists are hopeful about this new particle, the excitement could be premature. It's a common scientific pattern. Initial findings suggest something new, and then further testing either diminishes its importance or disproves it entirely. If further research confirms Z prime, it would indeed be a monumental discovery, but the road to such confirmation is long and filled with hurdles. The enthusiasm around Z prime reflects a broader desire among physicists for new findings that could lead to significant advancements. The field has seen its share of both groundbreaking discoveries and notable missteps. Whether Z prime will end up redefining our understanding of the universe or simply become another interesting research topic that didn't pan out remains to be seen. This situation serves as a reminder of the complex and challenging nature of pushing the boundaries of scientific knowledge. The process of scientific investigation is slow and methodical, demanding rigorous evidence before new theories are accepted. The narrative around these scientific endeavors tends to be filled with excitement and promises of groundbreaking discoveries. However, the reality of scientific research is much more gradual. Each experiment usually adds just a small detail to our big picture of the universe. For example, while the discovery of the Higgs boson was initially met with widespread excitement, subsequent research has mostly involved slowly piecing together how it interacts with other particles and forces, revealing that we still don't understand. Similarly, the quest to understand dark matter illustrates this slow pace of progress. Despite years of intensive research, we still don't really know what dark matter is made of. Every experiment seems to rule out some theories while suggesting new possibilities, keeping us in constant anticipation and uncertainty. Another area where hopes are high is the dream of unifying all fundamental forces under a single theory. While the idea is appealing and elegant, achieving this unification remains a theoretical pursuit. Despite its success, the existing standard model of particle physics doesn't cover everything, and the remaining gaps are significant. This pursuit of unification is driven as much by a desire for simplicity and order as it is by empirical science, reflecting our preference for neat solutions. What do you think about the ethical implications of pursuing such profound scientific knowledge? Like, comment, and subscribe to join the conversation and share your views.